The present video is aimed at producing a brief introduction to the idea of probability distribution so we can use some of them in SMath Studio with the Statistical Tools plugin. But it's not going to be a whole lot about SMath Studio, mostly about the
probability distributions are mathematical functions that are used to model random variables. Random variables, on the other hand, are variables associated with processes that involve some probability in their operation. According to the type of data that you can collect for those variables, they are classified as discrete and continuous. The number of passengers in a train, for example, is a discrete random variable because you can only count them one by one. In other words, in discrete values. The number of defective products that are being produced in a batch in a factory is also another example of a discrete random variable. For continuous random variables, we'll have variables that involve probability, but they can be measured in a continuous scale. For example, the maximum daily temperature in a location or the discharge in a river. For writing probabilities, it is commonly accepted that the name of the random variable will be shown as an uppercase letter, whereas the actual value that the random variable takes will be shown as a lowercase variable. Regarding discrete probability distributions, we have a function called the probability mass function that can be given as a table or as an expression that provides values of probability. The probability mass function actually represents the probability that the random variable takes a particular value. Associated with the cumulative with the discrete probability distribution, there is another function called the cumulative distribution function, or CDF. The probability mass function that we mentioned earlier is referred as PMF, but in many references it's still called PDF. There's an old name that used to be given to these functions that stands for probability density function. The cumulative distribution function is CDF, and that represents the probability that the random variable x is less than or equal a certain value x. If the random variable is such that the values that it can take go by 1, 1, 0, 1, 2, and so on, the cumulative distribution function will be given by the sum of the values of the point probabilities from the lower value up to the value of interest. This can also be written in terms of the probability mass function or probability density function as in this expression. For continuous random variables or continuous probability distributions, there is a function called the probability density function of PDF, and is typically given as an expression that can be used to calculate the probability of an interval utilizing this formula. The probability that the random variable x is between the limits a and b is the integral of a to b of the probability density function. There is also a cumulative distribution function, which is, as defined in the case of the discrete, is also representing the probability that the random variable x is less than or equal to x. In this case, however, is calculated as an integral going from the smallest possible value, which in most cases is equal to minus infinity, or in some cases we start with 0, up to the value of x of interest. We are going to use this property. The fact is that if you take this interval and make a equal to b, this is the same as saying the probability of x equal to a. There's only one value, right, in that interval. But when you integrate from a to a, this area gives you 0. So the probability of a point value in a continuous distribution is equal to 0. Give us the following result, because the probability of x equal a is exactly 0 and x equal b also is exactly 0. We may or may not include the limits of the interval in the definition of the interval. We could make it just less than, or simply not even include any equal to values in the intervals, and they're all going to be calculated using the integral that we point out before. Another result of importance is the fact that the probability of the interval a to b is equal to the difference in the values of the cumulative distribution function between b and a. In the Statistics Toolbox plugin in SMath Studio, they have predefined values of the PDF and the CDF of the following distributions: binomial, geometric, Poisson, uniform, discrete for the discrete distributions, Cauchy, exponential, normal, Rayleigh, uniform, and Weibull for the continuous. And for statistical inference, we have the standard normal, which is just another normal, but with mean 0 and standard deviation 1, student t, chi-squared, and the F distribution. Quantiles. Quantiles are defined by providing a probability such that the cumulative distribution function for a particular value of x is equal to p. The quantile is therefore the inverse function to the cumulative distribution function, or the ICDF, the inverse cumulative distribution function. And this is useful to generate random samples of data. With that, we finish this particular presentation.
The plugin Statistical Tools provides a number of functions related to the probability distributions presented. To produce a function, for example, these ones or these ones, you need to click somewhere and then click on the function icon and then on matrix and vector. Then you get a look for either PDF, CDF, or ICDF in alphabetical order. For example, you get here CDF.Cauchy, CDF.binomial. You also have down below the ICDF, the inverse, and finally the PDF in lowercase, PDF dot. These are examples, the PDF binomial. You can type it also if you know what you're looking for, PDF dot binomial, and then start providing the values that you want. So this is the PDF for a discrete distribution, the binomial, CDF, and the inverse binomial. For continuous, I have an example of normal, the cumulative distribution function normal, and the inverse cumulative distribution function normal. We are going to present those in more detail